Thank you for coming. My name is Deepak Singh. I run container services at AWS, and I've actually had the luxury pleasure of being at AWS for 8 years. Been with EC2 pretty much since the day I walked in and working on compute, which means that I've had, 8 years ago was 2008 when AWS was still very young. For those of you who weren't around or using AWS in those days and are very familiar with where things are today, there was no EBS, VPC didn't exist. You basically had C1 instances and an M1 instances in EC2, and you had S3, and I think that was it. So things have changed a lot, but what that has meant is that over those years, we've seen a lot of changes in the ways that people scale their applications. From the very early days of AWS, there was a very common pattern to scaling these applications, and fleets in general, but EC2 instances and applications are pretty much synonymous. A very common way of doing that would be to write an application with different components, wrap it up in something like a WAR file or a Rails app, run that Rails app on an EC2 instance that you thought would be a good instance for the good sized instance for the application, and then you would horizontally scale that application across availability zones in the AWS case where you had multiple AZs where your application was running to get availability, and then you would put it in an AutoScaling group, which wasn't also not around in 2008. People did that manually, but later AutoScaling came, and the most common, and it's still probably the most common way of doing things today, is you put your applications in an AutoScaling group, and you do two things with it. Either you manage the size of your fleet with AutoScaling by saying, hey, I want 20 instances running all the time, AutoScaling, please manage it for me. Or you wanted to reactively scale to traffic, and you would horizontally scale those on the instances that you're running your application on. Well and good. But the way people were writing applications started changing, and there are many, many examples of this. You've heard folks like Netflix give many, many talks about this pattern, is they started breaking these components that were part of their application out essentially into their own little applications. And 5 years ago, we used to call them single-purpose services or a service that you could run with one person or something like that. But this had a number of implications into the way people were thinking of scaling their fleets and operating their overall application, which is, one, in theory, you could write each component in its own language, use and run and deploy it the way you thought fit. You could also scale each component independently. So a common pattern that started emerging was you would have an application, you're probably running it in something like a JVM. The JVM would just run one service. You would either have 2 or 3 JVMs running on an instance, or you would run smaller instances and then just run many of them. And you would have many such sort of fleets that you would auto-scale independently. And that was all working really well. And into this world of almost exactly 3 years ago, just over 3 years ago, stepped Docker. And it's difficult to say if it's, which one came first, but I think Docker coming into this sort of microservices architecture, one fueled the other, and I think they ever had a symbiotic relationship since then. But let's talk about why Docker works really well for these kinds of applications. For those of you who are not familiar, my guess is, so who in this room has actually run containers on a single machine? Good. How many of you have run containers across many, many machines? Smaller number, good. Makes the talk useful then. So Docker is a form of what they call containers are a form of what they call operating system virtualization. A virtual machine in the sort of classic VM sense virtualizes hardware. You have many copies of your operating system and kernel on the same hardware, and each of them is isolated from each other. Containers work more in user space, where you're essentially getting isolation between user space processes using things like C groups and namespaces. But it gives you a very clear and clean way of separating these processes out. And containers have been around for a long time. From the very early days of AWS, customers like Heroku have been running their platforms on either directly on things like C groups or chroots or on things like LXC. But it wasn't until Docker came around that these things became very popular with a broader base. And the reason was that you actually had a way of packaging up these containers, which is a Docker image, describing it declaratively, which is your Docker file. So now you had a way of writing up what you wanted your application to be, what dependencies you wanted it to have, and you could package that up in an image. And then using the Docker CLI and the Docker tools, you could then run and deploy these containers. And the moment you could do that, you could automate a whole bunch of things. So what Docker did was essentially take all the capabilities that containers had and made them super easy to use and put them in a sort of packaging and runtime format that made them accessible to a much broader audience. And I think that's part of the reason things exploded. But as a result of those properties, you got a few other things. Docker and Linux containers are a feature of Linux, so they're relatively portable. You can run them on any machine that runs a modern Linux kernel. You can run the same thing in a virtual machine on your Mac and then run it on an EC2 instance. They are pretty flexible. You can describe them in different ways. You can have two containers. You can run a Red Hat container on top of an Ubuntu operating system. There's a lot of things that you can do. Because you don't have to boot the full operating system, you're running on the kernel, things move really fast. Second, most of these images are really small, tens of megabytes. I've seen gigabyte-sized images, but that's usually not the case. So they boot very quickly. And because you're getting fine-grained isolation, you're also using your systems more efficiently. Your hosts are much better packed. In theory, you can pack a number of containers onto a host, use the system resources way better than you could when you're trying to manage those processes on their own on an operating system. So you had all these properties. You could move fast. You could move quickly, which made containers a really, really good fit for microservices. Because of the way you could write your Docker files, and you could run essentially one service per container or on a small set of containers, you got the ability to model these services there's a number of ways that in the Docker world that you can do so, and we'll talk about one in a bit. You're not restricted by an application or a language. You could write your application in whatever language you wanted to. You had versioning kind of built into the platform. Your image is your version. They're mostly immutable. I say mostly because there are a couple of, the latest tag, in my opinion, makes things somewhat immutable. But you essentially could, every time you created a new image version, it was a new version of your image. You could test and deploy the same artifact. I think this is one of the things that people like a lot about Docker. Hey, I'm running this on my laptop. I'm going to run it in production. The same container should run without too many changes or any at all. And then because most applications and services in this world are stateless, you could do things like a new version is essentially a completely new deployment, and you're not trying to replace an earlier one or update it. You basically launch one in parallel, and then you kill the old one. It made the managing change much, much, much more easy. Now, none of these things are things that people were not doing before containers came around, but containers and Docker in particular just made this whole thing a lot easier. So I just asked how many people had run containers on a single machine, and a number of hands went up because it's pretty easy. There's a number of books out there that teach you to get started with Docker, and you can probably get started in half a night of work, and that's not very hard. But we started, about 2.5 years ago, we started having customers come to us and say, hey, we want you to build a Docker service. And I was in EC2 product management at the time. And it was kind of head-scratching, like, Docker runs fine on EC2. I launched a container or two yesterday. Why do people want us to build a service? So we started talking to them about what they really wanted to do. And it became pretty clear to us that people who wanted to run Docker in production weren't talking about running Docker on a single laptop. They were thinking of running containers much the way that run their EC2 instances, which means they want their applications to span availability zones. They want to manage the availability of these applications. They want these applications to scale based on various triggers and metrics, like things that you put in CloudWatch. They wanted to be able to decide what applications span zones, which ones can get packed into one availability zone. All these other features, all these things that you have to think about when you're running at scale. Deployments, updates, how do I route traffic? How do I put these behind a load balancer? All these questions started coming up, and people had started trying to do this on their own, and it was proving to be hard because no one really wants to run their own control plane. And that's one of the things that people want to avoid when they start using AWS in the first place. So we built ECS. So ECS was announced in November of 2014 at reInvent. And we launched a preview at that time, and then we went GA in April of last year, so just over a year ago. And there were a few things that we wanted to do. One was that we wanted to build a container management service. So all the management aspect of containers, hey, you should not need to run your own control plane. There should be a set of APIs, much the way you have with EC2, much the way you have with other AWS services, that allow you to manage the lifecycle and launch, stopping, getting the state of your system from your containers, right, without actually having to run anything. Second, ECS is also a scheduling platform. Allows you, through the built-in schedulers, to schedule these containers on a fleet of EC2 instances. And the third part was, we don't know everything. We don't understand every piece of way that people want to run these containers. So we should allow our customers to write and run their own schedulers. So those are sort of the three things that ECS is. But we had some specific goals that we wanted to solve based on what we had heard from the people that we had spoken to. The first one was to do container management at any scale. And what does that mean? The first one is something I've already spoken about. A lot of our customers were using some software package or writing their own. They were essentially building their own control planes, which is fine if you're running a small set. But if you're in an organization with many applications, tens of users, all of whom are deploying and running software whenever, in the ways they want to, perhaps multiple organizations within the same larger company, you don't want to run your own and operate your own control plane. You don't want to figure out how do I scale when I'm running 10,000 containers across 5,000 hosts, or even more, hundreds of thousands of containers. How do I scale my backend infrastructure? How do I scale my state management system? We didn't want people to worry about that, so that was goal number one. Second, we wanted to make sure that you got a very, very accurate state of the system whenever you wanted it, instead of trying to kludge up other ways of doing it, and that's a hard problem. We wanted to give you very fine-grained control and monitoring capabilities, and then last but not the least, whether you're running one or 100,000 containers, you shouldn't really have to change the way you are interacting with the service. The same APIs should just work. So that was goal number one. Goal number two was we wanted to have a lot of flexibility in how you actually place those containers, or which many people wanted to run long-running applications. That these are app services and applications that need to be highly available, that need to be always available. You need to be able to update them without taking downtime. Applications that many of you in this room probably run today. But people also wanted to run batch jobs. These are jobs that you've run once and they may not restart again, or they may run on a schedule. And in any organization, you have multiple types of applications with different characteristics. You want to run them all at the same time on the same infrastructure and not run a different cluster for each one of them. So we wanted to be able to support all of that. And I'll talk a little bit more about how we do that. And the third critical one was integration with the overall broader AWS platform, which is, how do I put my containers behind an ELB and route traffic to them? How do I manage health checks? How do I drain connections? How do I manage it when I'm updating a new version of that application? Can I have persistent storage with EBS? Can I run all of this inside a VPC? I want to be able to monitor this with CloudWatch, log changes to CloudTrail, be able to use IAM. These are some of the features that we have today. It's a much broader question, which is AWS is a much bigger platform, and I want my containerized applications to get the same benefits as you get with EC2 instances, to put it somewhat simply. So I'll talk about all of these things a little more detail, talk a little bit about the architecture of the system, why we have designed some things the way we have, and some of the core sort of features and capabilities of the system. And then we'll talk a little bit about how they manifest into running large applications. So the first thing I want to talk about is container management, which is sort of the core. When we launched in preview, this is pretty much all we did. We did not have any fancy schedulers. We didn't even have a console. We had a core set of APIs that really, really tried to give you very robust container management. And what does a container manager need? And for those of you who are thinking of going from running on one host to running on many, many hosts and running production applications in containers, this is something you will have to think about at some point. It is an essential requirement for what you want to do. You have a set of resources across all your machines. You want to be able to know what resources you have to use. You want to be able to track how the use of these resources changes over time. And anybody running a containerized infrastructure and who has run knows that these systems are very, very dynamic. Your containers have life cycles that some of them will run for days and others may run for seconds. And you have all of them happening at the same time. Your container manager needs to be able to accept or reject requests for resources. And last but not the least, you need to make sure that all of this information is being given to you accurately and it's consistent. You can't have a resource request and a second one come in, and because the system is not consistent, you say, hey, this resources are still available, but they're actually not. Result in very, very bad things. And here are some of the resources that you can track. And just to give you an idea of what a resource is, it could be CPU, memory, network ports, disk space. These are the ones that we do today. We don't do disk IOPS, but you could think of disk IOPS, and the same is true for network bandwidth, as resources that you want to manage. But really, there could be any resource that is finite that you want to be able to track and manage and control. You could define, there could be some arbitrary resource or something that you care about, like GPUs that we don't explicitly track today. So the way we do it in ECS is via the ECS Agent. The ECS Agent is available on GitHub. It's an Apache licensed service project. It's written in Go. You run it in ECS. It runs inside a Docker container. But really, you can build your own ECS Amazon machine image or AMI. Today, we provide you with one by default that comes with the agent installed and comes with an optimized version of the Amazon Linux AMI. But really, you can use any Linux OS that has the right version, the right Linux kernel. It has Docker running on it. And all you need to make it run with ECS is to have that agent running. You could make it part of the AMI. You could run it inside a container. You could bootstrap it. Once it comes up, it checks in, and then the service is under management of ECS. What the agent does is essentially it tracks these, it maintains these resources for you. It also tracks all the changes to the resources. And it does so by using Linux C groups constructs for the most part as exposed by Docker. It does a few other things as well. So here's kind of how it works. When an instance spins up with the agent on it, it registers itself against our control plane. It basically says, hey, I am an instance. I have 2048 is the amount of CPU shares that essentially means it's got 2 virtual CPUs on it. 1024 shares is 1 virtual CPU. And you're basically, this is just the CPU part. You'll have memory. You'll have other capabilities that are that are available through on an instance that you want to register against the service. But you can even do more interesting things. Let's say you have built an OS and you're running an agent on it of your own, or some other process that you don't want to be counted as the resources that you want to track. These are reserved resources. I want to keep them out of the system. You can actually modify them. You can reserve them and say, hey, 32 gigs of RAM, these UDP ports, these TCP ports, please don't manage them. I have them reserved for other purposes. Because you may be running some non-containerized application on that instance as well. And we won't manage it. But then you have to start modeling your applications into this world. And the way in the good old days you modeled it was you had a virtual machine, you had full operating system, and you ran your applications inside that. But now you're moving to much smaller slices. Something that could be made up of 1 or more containers. This is your little service or single-use application. It could be just a single container, or it could be multiple containers. Typically, we see 2 to 3 containers, but what we call a task definition. And a task definition is nothing but a declarative JSON syntax. We love JSON. So if you've seen CloudFormation or if you've seen an ECS task definition, you basically define the properties of all the containers that make up that task definition, any volumes that you might be using for it, and any other properties are all defined there. And basically, that is the information you're giving our control plane to say, hey, this is what I want this task to do. Please find a place to do it. And then you basically launch these task definitions onto a container instance, and a running instantiation of the task definition is called a task. And you can have 1 task or 1,000,000 tasks, which is just a copy of the same task definition running on your cluster. And everything in ECS happens in the context of a cluster, which is just a set of EC2 instances that get pooled together to form basically this blob of resources for you. The way you start a task is either the user using our StartTask API, or a scheduler, which is much more automated and has fancy business logic in it, basically calls our StartTask API. The StartTask API basically says, here's the task definition I want. Here's the number of copies that I need to run. Cluster management engine, is there a place for me to run them? The cluster management engine essentially sends this on to what we call the agent communication service, which writes it out to a WebSocket, which is how the agent communicates with the service, and says, hey, do you have resources that I need? And it actually knows where all the resources are, so it'll go to the right instance. The agent will then act that the task has been launched. If for some reason it can't launch that task, it'll let the control plane know, the cluster manager know that has not happened, and it can proceed on to the next request. The way you start a task is either the user using our StartTask API, or a scheduler, which is much more automated and has fancy business logic in it, basically calls our StartTask API. The StartTask API basically says, here's the task definition I want. Here's the number of copies that I need to run. Cluster management engine, is there a place for me to run them? The cluster management engine essentially sends this on to what we call the agent communication service, which is how the agent communicates with the service, and says, hey, do you have resources that I need? And it will then act that the Once the task runs, and this is kind of what it is, it essentially submits a state change, and the API is very intelligently called submit state change. And it basically registers that against the cluster management engine. You also want to, again, this is just how you make a resource request. But you also want to track all the changes in this resource request, and that can get interesting. Again, this is all managed through the agent that I just talked about and the system. But what happens when your EC2 instance is no longer available? So the happy case is that you shut down everything yourself. You submit a stop task API call. It gracefully shuts down all the tasks, clears out all the instances. You could even shut down your instance after that and basically say everything is clean, clear it out of the state or the system. Everything works well. But you have a network partition. You're running across 2 availability zones, and one zone, for some reason, goes offline. The task could be happily running, but essentially your agent has basically said you lose status. The cluster manager, when it polls the agent, says, can't find it, so I don't even know what's happening. What we've decided to do in ECS was the ECS service itself does not make any decisions for you, because we don't know what you want to do. Do you want to restart it? Do you want to let it die? Do you want to let it continue? That is something we've left to the scheduling layer to decide. That's where you write your business logic. The schedulers that we have written have some logic. You may choose to have some other logic. But all of that is taken care of in the scheduling layer. What your cluster manager is telling you is, I have no idea what's going on here. Please let me know what you want to do. And the third, there's probably more cases, more examples of what could happen. The third one is where you actually, there's some problem with the instance, but you know that, so you can, again, you can do the cleanup very gracefully for the most part. So you have all these changes happening. Again, with a single task, not a problem. It's not that hard. You could probably run a small database, track all those changes there, and everything would run just fine. But what happens when you're running many, many hosts and you have a very dynamic system? Things are changing every few seconds. How do you guarantee accuracy and consistency? So we'll talk about how ECS works underneath the hood. So we implemented ECS on top of one of Amazon's core distributed systems sort of primitives. It's something we've built over the years to meet the needs that not just ECS, but many of our other services do. And it's a Paxos-based transactional journal data store. So the way it works is, so any write that you do, any write to the data store is committed as a transaction on the journal, and it gets a specific order-based ID. And the state of the system is basically the sum of all transactions. And that's what's reported to you. And a read is just a snapshot in time of this, of the state of your system, which is basically a sum of all changes that you made over a period of time. So what this means is, for a write to succeed, the proposed write must be the latest transaction since the last read. So if you have a read that just happened and you have a bunch of writes coming in that happened along the way, if the ID is not after the last read, they'll basically be rejected and you have to retry. So what does this allow you to do? One, it allows you, this takes care of all our availability and scaling requirements because it's a primitive that we talk to, but it also allows us to build a completely optimistically concurrent system, which is super useful in a dynamic environment where you don't want clashes and you want clashes to be resolved very cleanly. So it's, I think, one reason that ECS is able to do things like scale the way it does, because nothing is pessimistically locked. This is something that we did about this time last year, so it's relatively old data. It's 2 days. We go from something like 200 instances to over 1,000. And the 2 lines you see are a 50th percentile API latency and a 99th percentile latency. And as you can see, once the system stabilizes and you have enough, statistically, you have enough data, you stabilize to about 25 milliseconds on the 50th percentile and about 75 milliseconds on the 70 to 75 on the 99th percentile. And that sort of stays stable independent of the size of the cluster. And you can take, you can build much larger clusters. And these are 1,000 hosts, not containers. You're running many, many, many more containers. But you get very, very good performance characteristics because of the transactional nature of the backend, which you don't have to worry about. It's just what we've chosen to build it on. You don't have to worry about how to scale it. You don't have to worry about, hey, how am I going to run what happens if I'm running my state management system in a single AZ, and that AZ goes away? What do I do? These are all things that we take care of for you. The next thing that we track is, next thing we'll talk about is scheduling. And again, scheduling calendars, as I found out, is a very, very hard problem, which is why you hire other people to do it sometimes. But what is a scheduler? Schedulers at their heart do a few simple things. They determine the desired state of the system. They check against the current state. And then they perform some action based on, hopefully, on something you've told it to do. And we'll talk about schedulers in general, but I'll use the ECS Service Scheduler, which is pretty much the way most people use ECS, as an example of how this works. So we call it a service scheduler. What is a service? A service models a long-running application. So you define a task definition. Hello? OK. Which could be like a front end, an application server, and maybe a small database, all of things that you want to place together. It basically maintains the desired state of the service. You tell it, I want 20 copies of this running, and make sure that there's 20 copies of it running by doing this sort of checking and making sure that things are working. And you can optionally run all of it behind a load balancer, an ELB, to route traffic appropriately. And so when you go into using the service scheduler, you go into our console, you see a much prettier version of this. In this case, you're basically saying my desired state is 5. I have 0 pending, and I have 0 running. Now, let's say that's what you enter. I want 5 copies of service number, ECS service version 1. You can tell it that I want 50% minimum healthy percentage, and I can have a maximum healthy percentage of 200. That's probably what you set as you go in. And it's a very simple state machine. You have a steady state. You determine your placement options. So for example, a few months ago, we launched the ability to be AZ aware, which means when you launch a new task, it's aware of the fact that your cluster could be spanning multiple availability zones, and it'll honor that. In fact, the default behavior is if you're running in 3 AZs, it'll try and keep the number of tasks running balanced across all 3. That's one example of a placement option. And as you can imagine, you can do a lot of interesting things there. And and then it deploys the task if it makes sure that things are working. So it's a very simple state machine. But what if you want to make some changes? And a change could be, as described here, you want to launch a new version, ECS service version 2, and you want to scale the service from 5 copies to 10 copies. Now, in this particular case, because your minimum healthy percentage is 50 and your maximum is 200, your 5 existing tasks can keep running, and you can actually launch you can have 10 tasks running at the same time, or actually more than 10 because you're saying your desired state is 10 and 200% of that is OK. And then basically, once all your new tasks are running of your new version, it'll drain connections from the original 5 tasks, and then move the ELB over to the new one. And it'll do it in a relatively graceful way so that you can do these sort of zero downtime deployments. And we've got, right now it's not, this whole process is controlled by our update API. You can do some other clever things if you integrate with other services. And this is just a way that the cluster manager is basically automating this for you. It knows the differences. It knows what state to get into. And basically, it's implementing this state machine. It's just one additional branch on your additional state machine. But that's something simple. I kind of went ahead of myself and talked about ELBs. You want to register and deregister against ELBs. You have permissions and error handling that you might want to do. Is the node even healthy? You might want to look at the health of your running tasks and do things based on those. You might want to scale down. And scaling down is important because you may want to do it in a way that doesn't create any conflicts. You may want to introduce some entropy into the system to make sure it's behaving properly. And this state machine won't fit into one slide, so here's a cartoon. So that's a single scheduler. But I think I talked about the fact that one of the core goals of ECS is to run multiple schedulers. This could mean 2 things. You have 3 different teams or 3 different applications or 3 different services, all using the service scheduler being launched on the same infrastructure. Or what's actually sometimes more common is you have a service and a set of batch jobs that you want to launch onto the same cluster. So the way this works is that each scheduler will basically periodically query the current cluster state to check for resource availability. So let's take in this case, your sort of orange scheduler. It makes a claim for the resources that it needs. The scheduler basically updates the state of the system, and basically this is a new transaction into that data store that I talked about. And when this next scheduler, it has an old view of the system because it already polled it, and it's trying to claim resources. And the system will basically say, hey, you don't have a correct state of the system, so you need to retry. Then it'll have to pick up a new state, and then it can make a claim for some new resources. So in general, this will always work. And you can do this with many, many schedulers. The more The differences between your individual schedulers, the better this will work. But as long as you're doing retries, you should be able to have multiple schedulers running without having conflicts. And these could trigger things like AutoScaling Groups. So we have a bunch of CloudWatch metrics at the task, at the service and cluster level that will basically say, hey, 70% of my cluster CPU is utilized. I need new hosts. And you could have, as your schedulers start scheduling tasks onto the cluster, you may start running out of CPU, and new EC2 instances will keep popping up underneath the hood to give you more resources to get for your applications. And you can decide which service actually triggers an auto-scaling action, and others that we may say, this service is not important, not that important, I don't want to spend more money on it, so don't auto-scale. If it can't find resources, that's fine. So what did we talk about today? We basically talked about the fact that as we think about new applications, containers add a number of interesting properties that make them super useful. You can break your applications up into tasks, and we call them task definitions. It's basically a declarative way of saying, here are these 2 or 3 or up to 10 containers that basically describe my application. I want to place all of these as one entity somewhere, and basically it's declarative. And because it's declarative, we have the ability to find the resources for it based on this complex architecture. But the best part about ECS is you don't have to build this complex architecture. You don't have to worry about the key value store. You don't have to worry about the cluster management engine. You don't have to design any APIs. These are all just things that are available to you. And what you have to worry about is what should your task definition look like, and what kind of scheduler do you want to use. If you're using the ECS Service Scheduler, you don't have to think about that either. But if you want to write your own scheduler, you can do so and run that, and then use it with ECS. And if you're a complex, if you're a large organization with multiple kinds of applications, that works you can do that as well. And we have a number of customers who do that. A good example of a customer that's built their own scheduling system is Meteor. So Meteor runs a service called Meteor Galaxy. It's their platform version of Meteor.js. And they built their own scheduler on top of ECS. So because they have certain business requirements that they need to fulfill. Coursera did something very similar. They have a very cool batch processing system built on top of ECS for giving people tests. They also happen to fork our agent because they have some very specific requirements because they don't trust any of their customers because they're all students who taking tests. So writing code, which makes them very dangerous. So these are just examples of customers who built their own sort of scheduling systems. Most of our customers just use the native schedulers as they are, and maybe add a thing or two here or there.